discussing two presentations from the Reinforcement Learning Conference. It's a new conference. I believe it was the inaugural conference, so this is pretty exciting. And I think two of the, in my opinion, big figures in reinforcement learning gave presentations. One is Sergey Levine, University of Berkeley, and the other is Dave Silver. He's with DeepMind. Both of them are, I think, pivotal in the field of reinforcement learning, Dave, because he created, I believe, the most important actual real-world example of how reinforcement learning can be used when he created AlphaGo and AlphaGo Zero and MuZero. I'm going to discuss a little bit later what that exactly is and why that's so important. And I think Sergey's contribution to the field of reinforcement learning is twofold. One is he really thinks about it very from a practical perspective in terms of what kind of data can be used or should be used or must be used to really take advantage of the reinforcement learning concept. And then I think his second contribution, in my opinion, is also he has this really nice feature that he always sort of he's very good at putting technical concepts in context with a bigger picture, and he gives you a good understanding of, let's say, where you stand relative to the rest of the field and what the field could do to advance and why it's important that, let's say, certain things are done that he's doing. For example, the offline reinforcement learning, why that's important from a big picture perspective. Not just, this is the project that I'm doing, this is my PhD, or this is what my graduate students are doing, so that's why it's important. No. It's really sort of a comprehensive view of the field. I think it's very useful particularly for people like us that are not in academia, but that need to understand what's going on in academia, because that's what we do at Orange Capital Partners. We try to understand what's going on in academia, where the technologies could emerge, and then how that can be translated into successful products and services. This is not even on podcast. It's November 12, 2024. This is Krim Telco for today. The fund is 8%. The market is flat for the year. We're up 61%. The market's up 25%. We're outperforming by 36%. So let's talk about Dave Silver first and then Sergey. So Dave Silver he was the lead engineer at DeepMind when they created AlphaGo. AlphaGo was a project where they created an AI that played Go, the playing game of Go, and they were successful in playing against the best humans and in fact beat the best humans and in fact even beat better models. And what's interesting about the AlphaGo concept is that you can see that Moore's law is at work here because more recent models are better than the older models. So more training actually makes those models better players, which I think is really, really interesting, just as a side note. Then he created AlphaGo Zero, which I think is, in my opinion, one of the biggest breakthroughs in AI, because what AlphaGo Zero is, it has no priors. So this model has never been taught the rules of Go. All it has been given is the constraints, and it also has been given the goal of winning. And by self-play in simulation, it has learned how to play and actually beat the best AlphaGo models, and also beats itself as more training is being used. So again, a very nice example of end-to-end learning, what we call end-to-end learning today, and most importantly also the fact that you can get better by training more, basically iterating more, shows that there is still, I guess there's still free energy to be reaped, if you will. Now, let me explain a little bit what reinforcement learning is from a big picture perspective and contrast it to LLMs. And Dave Silver does a really nice job because he talks about the LLM valley. And what he means with that is there is a curve that he's showing in the presentation. The x-axis is time, and y is popularity of reinforcement learning. And he shows that with AlphaGo and AlphaGo Zero, the popularity of reinforcement learning went very high up. And then with large language models, it came down, and now it's coming back up. And he's kind of saying, look, we want to get out of this LLM valley. We want to get back to prominence because reinforcement learning is important. Now let me contrast why is large language model the antithesis of reinforcement learning. It's not exactly the case, but that's how he's portraying. Well, if we just take a big picture view, is the following: the way the transformer architecture works, on which large language models are built on, it's it's a so-called maximum likelihood method. So what these models are doing is, in an unsupervised manner, they learn from data and they learn how to structure what they learn. In other words, they structure, it's kind of like a large database of clustered knowledge. And when you prompt a model like that, what it does in simple terms, it tries to match your prompt with the most likely cluster that it belongs to, right? So if I ask a question, it tries to predict the next word, and it does that by looking at its vast database of relationships between words and then figure out what's the most likely scenario under which the next word could be the best possible choice. So it's kind of a statistical game, if you will, where you look at, in statistical terms, it looks at distributions and it wants to find the prompt. So whatever you prompted it with, what's the birth, when was Napoleon born? What's the maximum likelihood that this prompt belongs to a certain distribution? In other words, the distribution of birthdays of Napoleon or birthdays of important people, and then within birthdays of important people, birthday of Napoleon, birthday being the day when you're born, and the date being the date when you're born, and so on and so forth. So it kind of matches knowledge. So what it really does, it maps what you ask it with its database of knowledge that it has stored in latent space, and that's what we need tokens for, and that's why we call it a tokenizer and things like that, because what we do is really we kind of compress the knowledge, in this case the knowledge of the internet, into a tokenized form in latent space. So what I think about it this way, maybe I'm sorry, I'm using words that might not make sense to most listeners. What I'm trying to say here is that think about it this way: like we take the knowledge of the internet and we represent it what's called in latent space, in some sort of other dimension, and that dimension is kind of like a highly dimensional vector space. And the knowledge, so the birthday of Napoleon, the height of LeBron James, the color of apples, the poems of Shakespeare, all of these things that are available, all that knowledge that's available on the internet is stored in vector form in the model. That's what the model actually is. It's stored knowledge. The pre-trained model, to be more specific, is really stored knowledge, stored cumulative knowledge of the internet. And then what we do is we prompt it, and it finds the most likely match with the prompt. So let's leave it at that. Again, this is not a technical podcast, so for people who are not satisfied with my technical explanations, please go and educate yourselves. There's plenty of opportunities online. And for those who are technically versed, they might think, okay, this is a little bit, maybe a bit better than a word salad, what you're doing here. But I hope to be able to convey that the game of transformers and GPT, which is sort of the most famous proponent of a transformer-based architecture model, is really matching statistically highly correlated items. Let's leave it at that, right? Now, what is reinforcement learning? Reinforcement learning is fundamentally different insofar as it doesn't just look at the way the world is, but it learns from interacting with the world constantly. That's the big difference. Now, just as a caveat here, at the margin, so if you really take this to the extreme, you could say that there's really not much of a difference between the maximum likelihood method under which large language models work and the, let's say, Q-learning, which is one of the most prominent algorithms under which reinforcement learning models work. But that's really in the sort of in the extreme. So it's like saying in the extreme French and English are the same thing. It's just sort of nuances. Certain words are pronounced differently, but the structure of the language is really the same, something like that. So it's really not the same when you use it practically, but theoretically, it's kind of the same thing. You use some sort of coded symbols and phonons to express knowledge and express intent and things like that. So back to AI. So reinforcement learning, I think the big difference is that reinforcement learning learns while it's interacting with nature or with something. Let's say in the case of AlphaGo, the way AlphaGo learned is by playing the game. So it wasn't just storing all the moves that people did and then created a database of knowledge of what happened when this is, what happened when that is. It learned while it was playing. Now again, at the extreme, you could say, well, in fact, that's really what it's doing, right? Every time it's exposed, what Q learning really is every time you're exposed to a new situation, you kind of go back into your database and you look, has something like this happened before? And if so, this is my move. So in a sense, it's very similar. But again, from a practical perspective, particularly when it comes to engineering and implementation, software development, it is really fundamental differences. Bellman equations, transformer architectures don't use Bellman equations. So the fundamental difference, again, in reinforcement learning is that you learn through interaction. And I think one of the most interesting ideas that I got from Dave Silva's presentation is that what's really useful in reinforcement learning is when you have a situation where there's a very clear ground truth. So, for example, he's using the case study of math, and they're using alpha, I think it's called alpha proof or something like that. Alpha proof, yes. So it's a model that is supposedly able to make mathematical proofs, and this model is trained on reinforcement learning. And the key advantage, according to Dave, in math in general is the following. Math gives you, particularly formal math, talking about formal math. So that's the kind of math where you make a statement and then you prove, and you make another statement and you prove. And the good thing about these things is that you can validate that. So when you make a statement, let's say you make a statement, and you then prove that statement. You can validate whether that proof is right or wrong. So that's really, really important. I'm going to come back to that, why that's important. But let's just leave it now. Let's just leave it linger for a second. Okay. So it's incredibly important to have a system where when the agent makes a move, it can be validated whether that agent is right or wrong. And there are other people working on, for example, the lady, the name eludes me right now. She's from Iran. She's a professor at Stanford. She has the large language monkeys. So that kind of project, for people who are familiar with that, go check it out. Just do a search, Stanford professor, large language monkeys. So she talks about the necessity to evaluate, in this case, large language models. But the point is this. I think in general, when you want to have an iterative approach towards learning, you need to have a validation method. In other words, you have to be able to say it's right or wrong. Now, this might sound trivial, but it's not so trivial because in many cases you don't have that. Let's talk about robotics for a second, right? In robotics, let's say driving, like self-driving, Tesla self-driving, full self-driving. Now, there is a ground truth, which is the database of driving the Tesla has, which I believe is the biggest competitive advantage Tesla has in AI today. They have a ground truth of driving. And this is incredibly important because let's say Waymo, Xpeng, and all these other companies, they are, they can have compute, they can have algorithms, they can have engineers a gazillion people working on mathematical formulas, but whatever they want to work on, they cannot do it. There's no restriction to that. But what you don't have is a ground truth of what does it actually mean to be a good driver versus a bad driver. This is really, really important, because if you want to evaluate the model, well, you have to kind of tell the model it's doing a good job or not. So whether you use some sort of unsupervised end-to-end type learning or reinforcement learning or something in between, we don't know exactly what Tesla is using, but you have to have a ground truth, and Tesla has this ground truth, and that is the database of driving that they've collected over years and years of monitoring people when they drive. So we, Tesla customers, have taught the Tesla model what good driving means. Now, good driving is human driving. And this is the first stage. According to Dave, this, what's called imitation learning, which is the concept that Tesla is using, is not going to make the Tesla robot, in case FSD, a superhuman driver. By definition, it's not going to be able to do better than humans because it's learning from humans. That's all it does. But we're very happy with having a driver that can drive us that's as good as a human. Now, if we want to go to superhuman driving, right, then we have to use something else, and that's reinforcement learning. And this is where Sergey Levine comes in his presentation. By the way, both presentations are on the show notes. Now, what Sergey is trying to do, in my opinion, one of the biggest contributions that Sergey is trying to do is really, on the one hand, create data sets for robot learning. That's a big proponent. That's a big part of his work. RTX, for example, which is the sort of a collection of data of robot data. Now, Sergey doesn't work on self-driving. He works on humanoid, let's say humanoid robotics. But anyway, so he's making a big effort in collecting data, standardizing the data, and then training models on that data. So that's one thing he does. And then the other thing is the offline reinforcement learning. So what does that mean? Well, if you take reinforcement learning at its sort of at base value, what is it? It's the robot or the machine interacts with nature and learns from mistakes. Now, ideally, you want to have this in simulation. This is what Dave Silver has done all throughout his career, and that's great. But unfortunately, we're not there yet with actual real-world AI. So when it comes to cars and humanoid robots, interacting with nature is still very difficult in sim because we don't have the physics figured out. We're getting there. I think there's a lot of work in actually representing, in the computer vision and 3D graphics, and all these areas are working all independently towards a cumulative model. I've recently met the CTO of ANSYS. Same thing. They're working on physics simulation. So this is definitely a problem that is first on top of the list of many independent companies and labs. And to me, that means that it's definitely going to get better. Maybe not so, but better. So that's one thing. So since we can't do sim, what can we do? And I think Sergey's approach in offline reinforcement learning is really a good idea, because what he's saying is the following. Look, we can't have a robot go out there and do stuff and break stuff all the time. So how about we collect data and we create this massive data set of, robots picking stuff, robots cleaning stuff, robots driving, robots flying, and so on and so forth. And then we use offline reinforcement learning, which is basically, think about it, you take that data and now you train the robot as if it was interacting with nature, but the interactions are relative to what you've stored in this offline reinforcement learning method. And maybe that's not a perfect training for the actual robot who's going to then actually perform stuff in the real world, but it's a good pre-training method. And maybe you can do a good sim to real adjustment, and you can go from there. So I think that's the main contribution of Sergey. There's a lot of technical problems with offline reinforcement learning, things like drift, distribution drift, and things like that. Think about it this way: if you train a robot to pick up stuff in let's say 50 different factory scenarios, but then in the 51st application of that robot is in a completely different factory scenario. The robot might not, be very well trained. So you kind of have to find fine-tuning methods. The other problem with reinforcement learning is that once you start drifting away from an optimal solution, you can then drift away for good. So in other words, let's say the analogy would be if I, try to paddle out for a good wave, and I keep maybe exploring and exploring, and I paddle to a little bit further out, a little bit further out. At some point, I could be way out there, completely off the break, and then maybe even in danger because now I just completely left the trajectory that was optimal for catching a good wave. And so in that sense, the analogy would be that you can drift away and then completely sort of not just not have an optimal solution anymore, but be way too far away to ever get back to the optimal solution. So what they developed with one of his grad students is called conservative RL. So that just means that you kind of try to, whenever the model starts drifting away from some sort of average track that it was on, you calibrate it so you keep it within a certain band and you don't let it drift away. So things like that. But anyway, that's technical stuff. Again, the presentation, Sergey's presentation, has a lot of papers listed for people who are interested in the actual technical capabilities. So to summarize, I think I want to say a few things. First, I think reinforcement learning is definitely a very, very important part of AI because it helps us not just make sense of the world, but also act within the world, which is very important for real-world AI. I think Dave Silver, in my opinion, is a very inspiring person, not just because he's done great things, but also he's one of those rare people who can really talk English, explain things, complex things in plain words, and help you really understand what's going on. I think his contribution in this particular presentation to me was really the importance of the validation, and I think that's something that I can see in the AI community. Validation is becoming more and more important, but I think Dave makes it very clear that if you want to make progress in reinforcement learning, you have to have systems such as, for example, math, formal math, where you have clear right and wrongs, so you can then use reinforcement learning to progress. And then Sergey's presentation at the same conference was about two really important things when it comes to reinforcement learning. One is data collection in the real world, and the other is offline reinforcement learning as a tool to bootstrap robotics. Thank you.